Hello everyone, we are solving problem 14 in this video. We are dealing with a practical application, a mass spectrometer. So we're saying that suppose the electric field between the electric plates and the mass spectrometer in the figure is E equals 2 times 10 to the 4 volts per meter, and the magnetic field is equal to 40 Tesla. The source contains carbon isotopes of mass numbers 12, 13, and 14 from a long dead piece of tree. To estimate the atomic masses, multiply by 1.67 times 10 to the minus 27 kilograms. So we have a couple of carbon isotopes. That means it's the same carbon atom, it's just with more neutrons. So it's a heavier nucleus if it has more neutrons. We heat them up, ionize them, select a certain velocity in the velocity selector, which is that place where we have a crossed electric and magnetic field. Then we accelerate them into a magnetic field where they orbit around, and we can tell what mass they are by where they land, the diameter 2r of their trajectory. From there, you can compare the different distributions, the ratios of isotopes to each other, and you can actually find out what the date of the tree is, so how old it is. So let's see, we have learned that when we set force of the electric field equal to force of the magnetic field, we can send a charged particle through this crossed electric and magnetic field, and it'll go straight on through. And we'll select only certain velocities, because if it was higher or lower, it wouldn't go in a straight line and it would curve off in some other direction. The nice equation that we get for this velocity is V equals E over B. If you don't know how we got this, ask me or check out the previous video about problem number 13. Okay, so if we find out what velocity these particles are coming out at, all we have to do is divide 2 times 10 to the 4 divided by 40, and we find that our special velocity in this case is going to be 500 meters per second. This is useful because we know that in the equation for a particle, a charged particle in a magnetic field that gets looped around like this, we say that that is centripetal force. So we set QB equal to mv over radius. If we want diameter, we just multiply radius times 2. So we need velocity. We already have mass from the previous description about multiplying whatever isotope number it is by 1.67 times 10 to the minus 27 kilograms. We have B, which is 40 Tesla. Q, it's a single charge, which means the charge will be 1.6 times 10 to the minus 19 coulombs. And all we have to do is solve for R. So some easy math here. All we do is multiply R on this side, and we divide by QB on the other side to get mv over QB. Go on ahead and plug in your numbers for M, V, Q, and B. And we will do this first for atomic mass number 12, carbon 12 as it's known. Okay, once you punch that in, we're going to want to double radius, because you can see up here, we are doubling radius, we're getting diameter, we're wanting to find out where exactly it lands. Let's say at this one spot. We want to find out how far away that is from the place where it shoots out of. And we will get diameter for isotope number 12 to be 3.13 microns, or micrometers, or 3 times 10 to the minus 6 meters. If you got that number, you are already on your way to a solution. Because what they're asking us is how far apart are the lines formed by a single charged ions of each type on the photographic film. So we can find the distance, the diameter of the path, which is, in this case for carbon-12, 3.13 times 10 to the minus 6. Well, we can follow this exact same simple procedure using this equation right here and solve it for number 13. So the diameter for 13, the only thing that will change is the mass right here. It's got the same velocity, 500. It's got the same Q, the fundamental charge, and the same B as listed above. Except this time for mass, we're going to do 1.67 times 10 to the minus 27 kilograms and multiply by 13. You should end up with 3.39 times 10 to the minus 6 meters. We are interested in the difference between these two. So the difference in distances, the spacing essentially between these two places where they land, ends up being 0.26 microns. So 0.26 times 10 to the minus 6 meters. If you want to just check this, you can go on ahead and calculate D14, and you'll find that it has the same delta D, which is 0.26 times 10 to the minus 6 meters, as these previous ones did between 13 and 12. So we see that kind of an important result, given the same velocity, the same magnetic field, that as we increase mass, we actually get a larger radius path. So if we were looking at our mass spectrometer over here, maybe isotope number 12 starts to land right here, isotope number 13 lands about here, and isotope 14 would land farthest away.